Talk about the hybridization of boron here. What's boron's hybridization in this particular product? We're going to fill it in this particular box. It started out as sp2. We made a new bond to it, a fourth bond to it. Think about carbon with 4 bonds to 4 different things. It's a hybridization if this was carbon. 1, 2, 3, 4 atoms attached to it. It would be sp3 hybridized. That's an important point. Again, this is good practice because we can revisit practicing formal charge, drawing correct Lewis structures, making sure we have enough electrons around things, calculating hybridization. So you see all these things you did on your first exam are the foundation of what we do moving forward. If any of them are weak, put a little star on it or highlight it right now. So you need to revisit this if you have some free time, right? If calculating these 2 hybridizations for these atoms was absolutely bonkers for you and you don't get it, you need to work on it. Figuring out the formal charge for these 2 atoms right here made no sense to you whatsoever. You need to work on those things because we're going to keep doing it. And my lectures will keep practicing them the proper way, but having the foundation is important. We're going to talk for about another 11, 12, 13 minutes, something like that. Then we'll take a break. But we're going to get to, I guess, what in our pre-lecture video was called case 1. This is the more common case for the Lewis acid-base definition and how we'll use it. And the good news is it's very, very similar to the Bronsted, how we look at it. This we're going to call the polar bond case. So there's 2 cases in Lewis acid-base definition. The last one doesn't even involve a proton. This involves an empty orbital. But this is the more common case. And this case, actually, is going to help us better understand why we push electrons the way we do. It's directly related to the Bronsted-Lowry definition. So it'll help us make sense of the Bronsted-Lowry definition. We're going to take a base and an acid. We'll take sodium hydroxide. This is going to serve as our base. We're going to take HF, hydrofluoric acid. This is going to serve as our acid. You should know that sodium hydroxide is a strong base from general chemistry. If you don't, make sure you know it moving forward. HF, maybe you don't know if it's a strong acid or not, but it's an acid. It's similar to HCl, which we just saw, so it has some similarity to HCl. Okay? And we're going to use the Lewis definition or Lewis way of thinking about these 2 particular compounds. Lewis is talking about pairs of electrons. Lewis base, electron, pair, donor. Lewis acid, electron, pair, acceptor. The reason the arrows have moved the way they have in the last example will be revealed right now. The Lewis acid, if we look at it very carefully, is a polar molecule. We have hydrogen and fluorine next to one another. Think which of these 2 atoms is more electronegative, hydrogen or fluorine? You should know right away that fluorine is the most electronegative atom in the periodic table. And if we were thinking about how this bond is polarized, it's polarized in this particular direction. Fluorine's more electronegative, so the electron density in this bond is going towards fluorine. And if we were to assign partial positive, partial negative charge to these 2 atoms, fluorine has a small delta minus on it, and hydrogen has delta plus on it. Delta in these cases means partial, just like from calculus. There's not a full +1 charge on hydrogen. There's not a full -1 charge on fluorine. That's not how formal charges work. But this molecule is very, very polar, and the electron density is distributed this way. And there's a partial plus charge on hydrogen and a partial negative charge on fluorine. This is a polar bond. This particular compound is a Lewis acid because it can accept a pair of electrons. It has a polar bond in it, and this polar bond is exactly how we can understand why the electrons move from here to here in this reaction. In sodium hydroxide, there's a negative charge here. There's a surplus of electrons. If these electrons are going to make a bond with our acid, are they going to bond with the atom that has electrons on it, or the atom that's already deficient in electrons because of this polar bond? The electrons move in a very, very logical way from high electron density to low electron density. And if we can identify a polar bond, and chances are we can identify an acid. If we take just this work right here that we're doing and apply it to the previous examples that we've done in our time together today, the arrows that I've been pushing from base to acid should make even more sense. So now that we've seen this, and you go back and restudy your notes later after our time together is done, the arrows should have this logic built into them. Electrons move from where there is high electron density to where there is low electron density. This arrow we also know means we're going to be forming a bond between these two things. Hydrogen had a bond, doesn't want two bonds, so if we form a new bond, this bond has to break. Which direction should this bond go? This bond is going to follow the dipole vector. It's going to go towards the more electronegative atom in the bunch. This is an equilibrium process. We'll talk about that later. It's not the most important part. But now is a chance again to correctly draw the products of this reaction. This first arrow means moving two electrons to form a bond. So oxygen should have a second bond to hydrogen. Something like this. We made water. Two pairs of electrons did nothing. They're still here. One oxygen-hydrogen bond, it was already there. One pair of electrons from sodium hydroxide formed a new oxygen-hydrogen bond. Maybe it's this one. The other species is really simple. We had F, we had three pairs of electrons we did nothing with, and it had a bond here. This bond broke, and we make fluoride here. If we really care, we can put sodium here, and we make sodium fluoride, but that part's really not that important for us. The key point is that we can illustrate and predict that this bond forms, and that bond breaks, and it follows this process of finding a polar bond. Let's do another one of these examples right away. We're going to do a slight modification of this. We're going to take ammonia, and we'll use HCl. Okay, take ammonia and HCl. One of these is an acid, one of them is a base. If you can pick which one of these is either the acid or the base, you're done. HCl should sound like an acid to you, so we're going to make a prediction that HCl is our Lewis acid. That would mean ammonia is our Lewis base. Between these two here, we're going to learn a quick way to determine acids and bases, but just from their names alone, you should know that HCl is a strong acid. Okay. This is our Lewis acid. We can see right away that this bond is polarized in this direction. Chloride is more electronegative than hydrogen. So the electrons here aren't shared evenly between these two atoms. We're going towards the more electronegative atom. That leaves a little bit of partial positive charge on this hydrogen and partial negative charge on this chlorine. And once we see this, then we know that the electrons are going to move from the base to the location in the acid where there's partial positive charge. This is going to be moving two electrons and forming a bond. Hydrogen doesn't want two bonds. It can break then, and these electrons will go to the most electronegative atom in the species. When this particular phenomenon happens, it's an equilibrium process. And we'll get back to equilibrium shortly. And if ammonia forms four bonds, such as this, it was neutral with three, you can calculate why and figure out for yourself. As it forms four bonds, it becomes formal +1 charge. Chloride, formal -1 charge in this particular electronic configuration. So this really helps, this particular slide in particular, as you study it, will help you understand why we've been pushing arrows the way we have throughout our first 40 or 50 minutes of lecture today. So as you study this particular slide, It will give you logic in each example we've done so far, the Bronsted-Lowry examples, etc., even the case 2 with the empty orbital case that we had right here. We have a species that wants electrons and a species that has electrons, and they go from one place to the other. I'm going to go back to just the first example very briefly, but this is how you should study it on your own too. This is back to our very first example today, our acid-base reaction with sulfuric acid and water. The arrows, once we can define which one is acid, which one is base, doesn't matter if it's Bronsted-Lowry or Lewis, the way that we're thinking about it. The acidic molecule has a polar bond in it. And I didn't draw this at the beginning on purpose, and you don't need to go back and re-annotate your notes now, but there's a partial positive charge on this particular hydrogen because this is a very, very polar bond. Hydrogen-oxygen is a very, very polar bond. Well, they exist here too, but we'll learn why this one is much more polar than this one. It has to do with the sulfur and all these oxygens here. So you can apply this thinking as you're going through and practicing redrawing the notes. Why are the arrows moving?